This is my Precalculus course. Today we're going to learn how to solve polynomial equations when the degree of the polynomial is greater than 2. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. A polynomial equation is an equation that sets a polynomial equal to 0. Here's an example in blue and an example in green. The solutions to a polynomial equation are called zeros because if a number is a solution, when you plug it into the equation, it makes this expression equal to 0. So we call the solutions, again, zeros. We also call the solutions roots. That's kind of a confusing term to use, but that's just another name that mathematicians give the solutions. And we can also call the solutions x-intercepts because if you graph a polynomial function like the purple one here, the x-intercepts are the numbers that you can plug in to make the polynomial equal to 0. Again, that's those are the solutions to a polynomial equation. Just be aware that if the solutions are complex or imaginary, then they don't represent x-intercepts because those are not numbers where the graph crosses the x-axis. Now, in previous courses, we studied quadratic equations like the one that you see here, or like the one that you see here. These are polynomial equations, but the degree is 2. And today we're going to focus on equations where the degree is greater than 2. And we solve these equations by using factoring or the quadratic formula. But when we have polynomial equations when the degree is 3 or greater, we're not going to use formulas to solve because the formulas are going to be too tedious to use. There are formulas for degree 3 and degree 4 polynomials, but they're too difficult to use. And when it comes to formulas for degree 5 and above polynomial equations, those formulas are too difficult to find, and some would even say impossible. So instead of using formulas, we're going to use something called the Rational Zeros Theorem. And it's difficult to explain this theorem without doing an example problem. So we're just going to do an example problem, get a picture of this theorem. We're going to use this for the rest of the class. So let's get right into example problems to explain how this works. Now notice that it says the Rational Zeros Theorem. So this theorem is going to help us to find the solutions to a polynomial equation, but it's only going to give us the rational solutions, or zeros. So irrational numbers are numbers like pi or root 3 or e. They are non-terminating, non-repeating decimals. Rational numbers are numbers like -2 or 5/3. So this theorem is only going to help us to find rational numbers. It will not help us to find irrational numbers, and it will not help us to find imaginary or complex numbers. So there are some polynomial equations where the solutions are only complex or they're only irrational numbers. So just be aware of that. Today we're going to study polynomial equations where all of the solutions are rational, and we'll worry about other examples in the next class. So here's how the Rational Zeros Theorem works. We're going to find the solutions to this equation, or the potential solutions. So P is going to represent all of the factors of the last term, and Q is going to represent all the factors of the coefficient of the first term. So just to be clear, I got this number from here, and I got this number from there. It's always going to be the coefficient of the first term and the last number that we're going to work with. And so I'm going to find the factors of 10. So we have 1, 2, 5, and 10. And the factors of 4 are 1, 2, and 4. So now I'm going to find all the possible options for P over Q. And I'm going to write plus or minus symbols for each one. So what this means is I'm going to take 1 in the first list, and I'm going to divide by all these bottom numbers on the second list. So 1 divided by 1 is 1. 1 divided by 2 is 1/2. And 1 divided by 4 is 1/4. So these numbers represent potential solutions to the equation. We don't know if these are solutions, but these are potential solutions. Now we have to keep going. We're going to divide 2 by 1, 2, and 4. So 2 divided by 1 is 2. 2 divided by 2 is 1, but we already have 1, so we don't have to write that again. And 2 divided by 4 is 1/2, but we already have 1/2, so we don't have to write that. Now we're going to divide 5 by all these numbers. 5 divided by 1 is 5. 5 divided by 2 is 5/2. And 5 divided by 4 is 5/4. And lastly, we're going to divide 10 by all these numbers. So 10 divided by 1 is 10. 10 divided by 2 is 5, but we already have 5. And 10 divided by 4 is 5/2, but we already have 5/2. So if there are rational solutions to this equation up here, they're going to be found on this list. So that's what the Rational Zeros Theorem does for us. It gives us a list of potential solutions if there are rational solutions. Now, it might be that none of these numbers are solutions to this equation. But if there are rational solutions, then they're going to be on this list. Again, we could have irrational solutions or complex solutions. In that case, none of these numbers would be solutions. Now, we're not going to solve this equation. We're not going to find the actual solutions right now. We'll do that later on in the class. Now we're just learning how to use the Rational Zeros Theorem. So notice we write plus or minus symbols on each of these because these numbers can be positive or negative. So let's do a couple more of these, and you can try some of these on your own. So right now we're just getting a feel for how the Rational Zeros Theorem works. So P represents all the factors of the last term, and Q represents all the factors of the first term. And so let's divide. So 1 divided by 1 is 1. 1 divided by 5 is 1/5. And 17 divided by 1 is 17. And 17 divided by 5 is 17/5. And again, notice that we write plus or minus symbols on all of these. So if there are rational solutions to this equation, they can be found on this list. Okay, so again, we're not going to use a formula like we did for a quadratic equation, a degree 2 polynomial. We're going to use the Rational Zeros Theorem. So let's try one more example before you try one on your own. So P represents all of the factors of the last term, and Q represents all the factors of the coefficient of the first term. So for 48 we have quite a few. 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. And 9, we have 1, 3, and 9. So there's going to be quite a few options here. So 1 divided by 1 is 1. 1 divided by 3 is 1/3. 1 divided by 9 is 1/9. And then we move on to 2. 2 divided by 1 is 2. 2 divided by 3 is 2/3. 2 divided by 9 is 2/9. So 3 divided by 1 is 3. And 3 divided by 3 is 1, but we already have 1. So don't worry, I'm not going to give you a problem where there's quite so many factors. So 3 divided by 3 is 1, but we already have 1. And 3 divided by 9 is 1/3, but we already have 1/3. So now we're going to divide 4 by all those numbers. 4 divided by 1 is 4. 4 divided by 3 is 4/3. And 4 divided by 9 is 4/9. And now we're going to divide 6. 6 divided by 1 is 6. And 6 divided by 3 is 2, but we already have 2 on the list, so we don't have to write that again. And 6 divided by 9 is 2/3, but we already have that on the list, so we don't have to write that again. And now 8 divided by 1 is 8. 8 divided by 3 is 8/3. 8 divided by 9 is 8/9. And 12 divided by 1 is 12. And 12 divided by 3 is 4. We already have 4 though. 12 divided by 9 is 4/3. But we already have 4/3, so we don't have to write that again. And 16 divided by 1 is 16. Again, I'm not going to give you a problem which has quite so many options here. 16 divided by 3 is 16/3. 16 divided by 9 is 16/9. And then 24 divided by 1 is 24. And 24 divided by 3 is 8, but we already have 8, so we don't have to rewrite that. And 24 divided by 9 is 8/3, but we already have 8/3 in the list, so we don't have to write that. And lastly, we're going to divide 48 now. 48 divided by 1 is 48. And 48 divided by 3 is 16, but we already have 16 on the list, so we don't have to write that. And 48 divided by 9 is 16 over 3, but we have that on the list, so we don't have to rewrite that. So these represent all of the potential rational solutions to this equation up here. If there are rational solutions, then they're going to be found on this list here. So that's how the Rational Zeros Theorem works. So I want you to try the next problem. Go ahead and take a picture of these two pages and attempt number 4. So you're going to write P and Q and P over Q, and remember that the last term is going to be what we use, and the coefficient of the first term. So this is where these numbers come from. And you want to find the factors, and then remember to write plus or minus symbols when you find the potential solutions to the equation. So try number 4, and when you come back, we'll do it together. All right, we're back. So the factors of 12 are 1, 2, 3, 4, 6, and 12. And the factors of 2 are 1 and 2. So now we're going to divide 1 by these numbers. 1 divided by 1 is 1. 1 divided by 2 is 1/2. And we're going to divide 2 by the bottom numbers. 2 divided by 1 is 2. And 2 divided by 2 is 1, but we already have that on the list, so we don't have to worry about that. And 3 divided by 1 is 3. And 3 divided by 2 is 3/2. And 4 divided by 1 is 4. And 4 divided by 2 is 2. So we already have that on the list, so we don't have to write that. 6 divided by 1 is 6. And 6 divided by 2 is 3, but we already have that on the list, so we don't have to write it. And 12 divided by 1 is 12. And 12 divided by 2 is 6, but we already have that on the list, so we don't have to write it. So these are all of the potential solutions, the potential rational solutions, that is, to the equation up here. So if you got those right, good. Again, we're not going to find the actual solutions yet. We'll do that in the next problems. So I want you to try number 5. Find all of the potential rational solutions to the equation, and when you come back, we'll do it together. Okay, we're back. So P represents all of the factors of the last term, and Q represents all of the factors of the coefficient of the first term. So 7 is prime, so we have 1 and 7. And 8 is going to be 1, 2, 4, and 8. And now we're going to find all the possibilities, or all the options, for P over Q. So 1 divided by all these numbers. So 1 divided by 1 is 1. 1 divided by 2 is 1/2. 1 divided by 4 is 1/4. And 1 divided by 8 is 1/8. Then we're going to move on to 7. 7 divided by 1 is 7. 7 divided by 2 is 7 over 2. And 7 divided by 4 is 7/4. And 7 divided by 8 is 7/8. So these are the potential rational solutions. We don't know if they're actually solutions. They're just possible rational solutions to the equation. So if you got that list right, good job. Okay, now I want you to try one more of these problems. Try number 6. And when you come back, we'll do it together. Okay, we're back. So P represents all of the factors of the last term, and Q represents all the factors of the coefficient of the first term. So just to be clear, that number came from there, and that number came from there. And we're going to find all the possibilities for P over Q. So for 50, we have 1, 2, 5, 10, 25, and 50. Those are the factors. And for 1, we have just 1. So now we're going to take all these numbers and divide by the number on the second list. So plus or minus 1. 1 divided by 1 is 1. 2 divided by 1 is 2. 5 divided by 1 is 5. 10 divided by 1 is 10. 25 divided by 1 is 25. And 50 divided by 1 is 50. So those are the potential rational solutions to that equation. So if you got that right, good job. So now we're going to actually learn how to solve polynomial equations using the same theorem that we just learned. So you should have a pretty good idea of how the theorem works. Now let's actually use it to solve an equation. So let's use the Rational Zeros Theorem to see if we can find the actual solutions. Again, we know how to find the potential solutions, but we'll actually determine what the solutions are now of this particular polynomial equation. And again, we're going to use the Rational Zeros Theorem to do that. So the factors of 8 are 1, 2, 4, and 8, and the factors of 3 are 1 and 3. And now we're going to find all the potential rational solutions. So 1 divided by 1 is 1. And 1 divided by 3 is 1/3. And 2 divided by 1 is 2. And 2 divided by 3 is 2/3. 4 divided by 1 is 4. And 4 divided by 3 is 4/3. 8 divided by 1 is 8. And 8 divided by 3 is 8/3. So these are the potential solutions to the equation. But now we're actually going to test these numbers. Fortunately, we're not going to have to test all of them, but we're going to start to plug in numbers into this equation to see if any of them are actually solutions. So we always start with 1 because that's the easiest number to deal with. We're going to try x equals 1. And so I'm going to go ahead and substitute 1 for x. So we have the following expression, and you're not going to have to actually show this work. I'm just doing this so you can see exactly what is happening here. So we're going to see if this equation is actually true. So we have to use the order of operations. 1 to the 4th power is 1. 1 to the 3rd power is 1. 1 to the 2nd power is 1. 22 times 1 is 22. And then we have 3 minus 16 plus 11 plus 22 minus 8 is equal to 0. 3 minus 16 is negative 13, plus 11 is negative 2, plus 22 is 20. 20 minus 8 is 12, so 12 is not equal to 0. So 1 is not a solution to this equation up here. So remember, these numbers represent the potential rational solutions. So that was not a solution. So now the next number that we typically use is negative 1. We're going to see if negative 1 is a solution to the equation. So we're going to plug in negative 1. And now let's see if that is a solution. So negative 1 to the 4th power is 1. Negative 1 to the 3rd power is negative 1. Be careful with your signs. Negative 1 to the 2nd power is 1. 22 times negative 1 is negative 22. And then we have 3 plus 16. Again, be careful with your signs. So 3 plus 16 is 19. 19 plus 11 is 30. 30 minus 22 is 8, and 8 minus 8 is 0. So we get 0 is equal to 0. So negative 1 was a solution. That's a solution to the equation above. So we found one of the solutions, but at this point, we have a couple questions that we need to ask. The first question is, how many solutions are there? Is negative 1 the only solution, or should we look for more? Well, it turns out that there's a theorem that tells us that if we have a polynomial of degree n, the polynomial has exactly n zeros, or solutions to the equation, if we set it equal to 0. And those solutions can be real or complex, or they can be what we call repeated. We'll talk about what that means later on. So for example, if you have a 4th degree polynomial equation, then there's exactly 4 solutions to that equation. Now again, the solutions can be complex, they can possibly be irrational or rational, or they can be what we call repeated. So what that means is we have to keep looking. We need to keep looking for more solutions. We found one, but because this is a 4th degree polynomial, we have 3 more that we have to worry about. Now, are we going to keep plugging in more numbers as we did in the first step? That makes sense, right? That's what we did to find the first solution. Why don't we just keep plugging in more numbers to find the other solutions? Well, we could do that, but it's a lot easier to use some other tools to find the remaining solutions rather than just plug in numbers, because we certainly don't want to have to plug in these fractions, and we're actually never going to do that. I'm never going to make you plug in a fraction to this, because that would be very tedious to have to do those calculations. So it's just not realistic to keep plugging in numbers to find the remaining solutions. You're going to find the first solution, and then you're going to use that solution to simplify this problem so we can find the other solutions. So that leads us to something called the polynomial degree factor theorem. To be honest with you, a lot of these theorems don't have names, but it's hard to memorize them if they don't have a name. And by the way, we're doing advanced mathematics now. This stuff is very, very advanced. It took hundreds of years for mathematicians to learn these theorems, or to simply prove the theorems. But even though the proofs are pretty rigorous, the general idea is actually very easy, the ideas that we're seeing here with these theorems. So if there are n zeros for a polynomial equation of nth degree, then you can imagine that we would be able to factor polynomials into products of factors of this form here. And this theorem that we learned up here is actually kind of a result of the polynomial degree factor theorem. So notice that we have, in this example, a degree 3 polynomial, and we factored it to 3 expressions of that form in green. That's going to be true for every polynomial equation, a degree 1 or degree 2 or 3 or 4 or 5 or 6, whatever the degree of the polynomial is, you're going to have that number of factors. Again, in this case, we had a degree 3, so we have 3 factors. And that's why there's going to be exactly n solutions for an nth degree polynomial equation. Because if you plug in a pink 6 here, then it makes the expression 0. If you plug in an orange 2 or a negative 4/5 in the purple, those are going to be solutions to a polynomial equation if you set this expression equal to 0. So that's a very, very useful tool, along with this theorem up here. And that leads us to the factor theorem. So let's say that f is a polynomial function. If you plug a number into that polynomial and you get 0, then x minus that number is a factor of f of x. So again, that's just a result of what we said up here. So the polynomial that we're trying to analyze, the polynomial equation that we're trying to solve, we're going to write the polynomial here. And we know that if you plug in -1 to this green polynomial, you get 0. We found that using the Rational Zeros Theorem. But if you plug in -1 and you get 0, then by the factor theorem, that means that x minus -1 is a factor of this polynomial here. So you can actually factor x minus -1, but be aware, of course, x minus -1 is the same thing as x plus 1. You can factor x plus 1 out of this green expression. So if you factor, you're going to get some function g of x times x plus 1. And what we're going to do is we're going to divide by the blue x plus 1, and that's going to cancel out that x plus 1, and you're going to be left with a function or an expression that's a polynomial, and that expression is going to be a lot easier to deal with, and it's going to help us to find more solutions. Furthermore, g of x is going to be a polynomial that has a degree 1 less than the degree of the green polynomial. And how do I know that? Well, it's actually pretty easy to show. If we divide by x plus 1, we're going to get, again, some function g of x. And if we multiply both sides of this equation by x plus 1, we get x plus 1 times g of x is equal to this original polynomial that we have in our equation. So if you analyze this equation, if you multiply g of x by x plus 1, well, there's only one x here with a power 1x. So you're going to increase the degree of g of x by 1 to get this polynomial here. So that proves that g of x must be a polynomial with degree 3, one less. So it's kind of just common sense. It seems hard to show that, but it's actually common sense. So we're going to, again, find that polynomial. It's going to be a polynomial with a degree 1 less than the degree of this polynomial, and we're going to call that a depressed polynomial. And we're going to use that to find more solutions to the equation. Again, we found one solution. Now we have to find 3 more solutions because we know there's a total of 4. So we're going to use long division to divide, but the problem is we don't want to use long division because that takes a lot of work, takes a lot of writing. But because we're dividing by a binomial of this form, remember, we can use a faster method, synthetic division. And because we're always going to be dividing by a binomial of this form, we can always use synthetic division. So this process is going to go a lot faster. So let's bring this polynomial up so we can set up our synthetic division algorithm. So we're going to divide by -1, so I'm going to write, well, actually we're dividing by x plus 1, but remember, it's going to be the opposite sign when you use synthetic division. I'm going to write the coefficients. And so now we'll use synthetic division. We're going to drop the 3. And then we're going to multiply these numbers to get -3. And then we're going to add these numbers to get -19. Then we're going to do the whole thing over again. We're going to multiply these numbers, and we get 19. Add these numbers, and we get 30. Then we're going to multiply these numbers, and then add these numbers. And then we're going to multiply these numbers, and add these numbers, and we get 0. So remember that this number always represents the remainder after you divide. Now we have an important theorem called the Remainder Theorem that says that we're going to let f equal a polynomial function, or it's going to be a polynomial function. And if f of x is divided by x minus c, in our case x minus -1, then the remainder is f of c, in our case f of -1. So you don't really have to worry about the proof of this theorem, but what that simply means is that our remainder should be the value that you get in the function or the polynomial when you plug in -1. So we know when we plugged in -1 to this polynomial, we got 0. So that's what you should see here. I know that seems kind of complicated, but all you have to know is if we did all the math correctly, then we should have 0 here. So that's kind of an extra fail-safe. It's a check for us. So now we can write what we call a depressed polynomial. Here we have degree 4, but now we have a degree 3 polynomial. And we got these numbers from there. So again, notice that the degree is 1 less than the degree that we started with in our original polynomial. So what this means is that our original polynomial in our equation is equal to x plus 1, because one of our solutions is -1. We found one of the solutions is -1, times 3x cubed minus 19x squared plus 30x minus 8. Okay, so we factored out x plus 1. And remember, by the polynomial degree factor theorem, we can create 3 more factors, because there's going to be a total of 4 factors, because this is a degree 4 polynomial, and there's going to be 4 solutions. You can see that if you plug in -1, it's going to make this whole thing 0. So now we need to check for what we call repeated zeros. We plugged in -1 to the original polynomial, but now we're going to plug in -1 again to this pink polynomial to make sure that this factor is actually not going to be repeated. So let's do that. Let's try x is equal to -1 again. And so now we're going to plug this number into, again, the depressed polynomial. We're not going to plug it into the original. We're going to plug it into the depressed polynomial, because that's going to be easier to deal with. Again, that's the whole purpose of doing this, so we don't have to deal with a 4th degree polynomial. So we're going to see if that expression is equal to 0. So let's make sure that we plugged in everything correctly. So -1 to the 3rd power is -1. -1 to the 2nd power is 1. 30 times -1 is -30. And then we get -3 minus 19 minus 30 minus 8. And you can see that that's not going to be correct. There's no way that that could possibly work. So we don't have a repeated, at least -1 is not a repeated 0. So now we need to go to our list to find some other numbers that we can plug in, some other potential zeros. We tried +1 and -1. Now again, we don't want to plug in fractions, because that's really difficult to have to deal with. So we're going to try +2. So 2 is on our list of potential zeros, so let's try that. And again, we're going to plug into our depressed equation, not the original equation. The original equation is a 4th degree polynomial. We want to deal with a 3rd degree polynomial. It's the easier, the depressed polynomial, the pink polynomial up there. So let's do the math. Whoops, that should be a 2 there, sorry. So we're plugging in 2, and we get 3 times 8 minus 19 times 4 plus 60 minus 8. And then we have 24 minus 76 plus 60 minus 8. And don't be afraid to use your calculator. There's nothing wrong with using your calculator. So 24 minus 76 is -52, plus 60 is 8, and then 8 minus 8 is 0. So we don't have a lot of room there, so I'm just going to write 0 is equal to 0. So that worked. So now we know that 2 is another solution. So now we're going to take the depressed polynomial and we're going to divide by x minus 2. Because again, if you plug in 2 and you get 0, that proves that x minus 2 is a factor of the function. So we're going to divide by x minus 2 instead of x plus 1 that we did in the first step. And that's going to cancel out that factor. But when you divide by x minus 2, again, you write a plus 2 in the algorithm there. So I'm going to take the depressed polynomial and divide that by x minus 2. So let's bring that up real quick, or bring it down. So the coefficients are 3, negative 19, 30, and negative 8. So let's do the algorithm. And our remainder is 0, and that tells us that we are on the right track. Because remember, the remainder is this number here, and that should be the value of the polynomial when you plug in 2, and we already found that the value is 0. So that means that we're doing everything correctly, and now we have an even more depressed polynomial. So now we have a degree 2 polynomial. We went from a degree 4 to a degree 3, and now we have a degree 2 polynomial. So we're making the problem more and more simple, easier to deal with. So this is just reminding us of the factor theorem again. So now we can say that this fourth degree polynomial, the polynomial that we started out with in this problem, it is equal to x plus 1, because negative 1 is a solution. We found that in the first step, times x minus 2, because we just found that 2 is a solution to the equation, times the blue 3x squared minus 13x plus 4. So we use the Rational Zeros Theorem to find the first solution, negative 1. Then we use synthetic division to find a depressed polynomial, and we then found another solution, 2. And now we're just going to use our basic knowledge of quadratic expressions to factor and find the third and fourth solution. So let's factor that blue polynomial. It's a quadratic. So 3 times 1 is 3. And these two numbers have to be negative, so let's try negative 2 and negative 2. They multiply to 4. But if you FOIL this out, it's not going to work, so let's try something else. Let's try 4 and 1. Looks like that is not going to work, so let's try switching the numbers. And that works. So what does this tell us? It tells us that our solutions are x is equal to negative 1. That's the x plus 1 factor. 2, that's the x minus 2 factor. 1/3, that's this factor here. And 4. So that is the final answer to the problem. There was actually 4 solutions because, again, it's a degree 4 polynomial. So just to be clear, what happened here, we had a polynomial equation, and we took this expression here and we factored it into a product of 4 factors. And what that means is we can see the solutions to the polynomial equation. Because again, we set the polynomial equal to 0 in the equation. So if you plug in -1, you get 0. If you plug in 2, you get 0. If you plug in 1/3, you get 0. If you plug in 4, you get 0. So just to be clear, what we did is we took this polynomial expression and we changed the form into this yellow factored form. And now we can see the solutions. If you plug in 4, you get 0. That's a solution. If you plug in -1, that's a solution because you get 0. If you plug in 2, you get 0. So 2 is a solution. If you plug in 1/3, you get 0. So that's a solution. So again, because we have a degree 4 polynomial, there's going to be exactly 4 factors. Okay, so let's try another one of these problems. This problem is stated a little differently, but it's really the same problem. It says use the Rational Zeros Theorem to find the roots of the polynomial function below. Now remember, a root is just a solution to a polynomial equation. It's the same thing as a 0. You can call them zeros or roots. And if you find the zeros or the roots of a polynomial function, you're just finding the solutions to the corresponding equation if we let f of x be 0. So it's just stated in a slightly different way, but we're still going to use the same methods. So we want to find the x values that will make this expression equal to 0, so we're going to use the Rational Zeros Theorem, like we did in the first problems. So P represents the factors of the last term, so that would be 1, 3, and 9. Q represents the factors of the coefficient of the first term, so that would be 1 and 2. And then we're going to find all the potential rational zeros, or roots, whatever you want to call them. So 1 divided by 1 is 1, 1 divided by 2 is 1/2. So we divided these. And then we're going to divide these. 3 divided by 1 is 3. And 3 divided by 2 is 3/2. And 9 divided by 1 is 9. And 9 divided by 2 is 9/2. So these are the potential rational zeros, or roots, or x-intercepts, whatever you want to call them. So now, again, we're going to start with 1. We always start with 1, so we're going to plug it in to this expression here and see if it equals 0, and it does not equal 0. So now we're going to go to -1, plug it in, see if it equals 0, and it does not equal 0. So we tried 2 potential solutions, they didn't work. So now let's try to plug in 3, because again, we're not going to plug in fractions. We're going to try to avoid fractions. Let's try plug it in 3. We're not going to plug in 2 because 2 is not on the list. So let's try plug it in 3. And when we do that, we see that 3 is a solution. So remember, the factor theorem tells us that if you plug in 3 and you get 0, then x minus 3 is a factor of f of x. So there's a factor x minus 3 in this yellow polynomial, and if we divide by the blue x minus 3, it's going to cancel it out, and we're going to end up with a depressed polynomial. But again, we're not going to use long division. We're going to use synthetic division because it's much faster. Remember, you can use synthetic division when you have a binomial of this form. So let's write our coefficients. And we're dividing by x minus 3, so we're going to write positive 3 there. And we get 0, so we should get 0 because the remainder represents the value of the function when you plug in 3. And we already found that that's equal to 0 up here. Okay, so now we have a depressed polynomial that we can generate. We have a degree 3 polynomial, and we're going to go down to a degree 2 polynomial. Remember, you always go down by one degree. So what this means is that our original polynomial is equal to x minus 3, because we found 3 is a solution, x minus 3 times 2x squared minus 5x minus 3. So that's that green polynomial there. And now, because this is a degree 3 polynomial, we don't really have to do that again. We can just factor the quadratic, and we'll be pretty much done with this problem. So 2 times 1 is 2, and let's try 1 and 3. And that doesn't work, so we'll have to change the signs. Let's change the negative to a positive and the positive to a negative. And there we go. So now we have successfully factored, and notice that we have a degree 3 polynomial. That's what we started out with. And we have now factored to a product of 3 binomials. So again, that's the polynomial degree factor theorem. If you have a polynomial of degree n, you can always factor to a product of n factors of this form. So now we can see the numbers that you can plug in to make the polynomial equal to 0. You can plug in 3. So x equals 3, or x equals -1/2, or x equals 3 again. Now notice that there are 2 x minus 3 factors. So that means that 3 is what we call a repeated root, or 0, repeated 0. You could say that it's a repeated solution, although that doesn't really make a lot of sense. Remember that if you have a degree n polynomial, there's going to be exactly n solutions, but some of those solutions might be repeated. So you could say that we have 3 solutions, but one of the solutions is repeated. Now, I know what you're thinking. You're thinking, that's kind of dumb. We don't have 3 solutions. We have 2 solutions. Well, yeah, we do have 2 solutions, but again, just to make the concepts easier to understand, we consider this solution to be repeated. So technically, based on our polynomial concept, we do have still 3 solutions for a 3rd degree polynomial. Now we're going to learn something called the multiplicity of a 0. The multiplicity of a 0. If a 0 is repeated m times, then the multiplicity of the 0 is defined to be m. So this 0 was repeated twice. We have x minus 3 twice, so the multiplicity of that 0 is 2, because again, there's 2 of these factors. So for example, if you have a function that can be factored like so, you see that 7 is going to be a 0, because if you plug in 7, it's going to make this whole thing 0. If you plug in -2, it's going to make this whole thing 0. If you plug in 4, it's going to make the whole thing 0. So 7, -2, and 4 are zeros of the function. But 7 is a 0 of multiplicity 2, because you can see that there are 2 x minus 7 factors. -2 is a 0 of multiplicity 3, because there are 3 x plus 2 factors if you write in the exponential form. And 4 is a 0 of multiplicity 1, because there's only 1 x minus 4 factor. So you can put the function, the factored function, in exponential form, and the exponents represent the multiplicity of the corresponding 0. Okay, so let's try another problem. This problem again is stated a little differently. It says use the Rational Zeros Theorem to find the zeros of the polynomial function. Rather than calling them roots, it's calling them zeros. And it says write the multiplicity of each 0. So we haven't written the multiplicity of the zeros in the first 2 problems that we did, but now we're going to write the multiplicity. So we're going to start by using the Rational Zeros Theorem, as we did in the first 2 problems. That's going to help us find the potential zeros, the rational zeros. So P represents the factors of the last term, 6. And Q represents the factors of the coefficient of the first term, which is 1. So just to be clear, we got that from there and that from there. The factors of 1 are simply 1. So we're going to divide all these numbers by 1 to find our potential rational zeros. So 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. Okay, so now we're going to test some of these numbers. So let's try plugging in 1, and it worked. 1 worked. So 1 is it's a 0. We found one of the zeros. So we're not going to keep plugging in these numbers because that would get kind of tedious. So now we're going to use the math that we learned previously. We're going to use synthetic division, and we're going to divide by x minus 1. The factor theorem tells us that if 1 is a 0, if you plug in 1 and you get 0, then x minus 1 is a factor of this polynomial. So we're going to divide by x minus 1 and figure out a depressed polynomial that's going to help us solve the rest of the problem. So let's write the coefficients. We have 1, -4, -12, -2, 11, and 6. And now we're going to use our synthetic division algorithm. And our remainder is 0, so that's a good sign. So now we have a depressed polynomial. We started out with a 5th degree polynomial, so now we're going to be going down to a 4th degree polynomial. This is going to be easier to deal with. So now we're going to try to find repeated zeros. So remember, if 1 is a 0, then it's possible that 1 could be a repeated 0. So we're going to plug in 1 again, but if you do that, you're going to see that it's not a 0. It doesn't work. So now we're going to determine if there's any repeated zeros. We're going to plug in 1 again, but now we're going to plug it into the depressed polynomial. And when we do that, we're going to see that that is not a 0. That doesn't work. But if we plug in -1 into this depressed polynomial, we see that it does work. So again, based on the factor theorem, that tells us that x plus 1 is a factor of this pink polynomial. So if we divide by x plus 1, we can reduce it to another depressed polynomial. So let's use synthetic division. And we're going to divide by x plus 1. And the coefficients are 1, -3, -15. 1, -3, -15, -17, -6. So let's use our algorithm. So the remainder is 0, so that's a good sign. And now we have another depressed polynomial. So we started out with a 5th degree polynomial, we went down to the pink 4th degree, and now we're going down to a blue 3rd degree polynomial. So now we'll check for a repeated 0, so we're going to plug in -1 to this depressed polynomial, and it turns out that that is actually another 0. So now we can take that depressed blue polynomial and divide by x plus 1 again. All right, so let's do the algorithm. And our remainder is 0, so again, that's a good sign. That means that we are doing this correctly. So now we have a 2nd degree polynomial, and things are getting much easier now. So therefore, we can say that the original polynomial, which was a 5th degree polynomial, is equal to, what was the first 0? The first 0 was 1, so it's equal to x minus 1. Then we had x plus 1 as a factor, and x plus 1, because we found 1 worked, and that was a 0, and -1 worked, but it worked again. And lastly, we have the green quadratic factor that we haven't factored yet. So now, let's factor that green quadratic. So what two numbers multiply to -6? And they add up to -5, so that's going to be -6 and 1. So we can put this in exponential form, so we have x minus 1 times x plus 1 to the 3rd power, because there's 3 of those factors, times x minus 6. And so we can see the zeros just by looking at this expression. We changed the form of the polynomial from the blue form to the yellow form. So we can see, looking at the yellow form, what numbers that we can plug in to give us 0. We can plug in, obviously, 6. We can plug in -1, or we can plug in +1. And that'll give us that'll be solutions to the corresponding polynomial equation. So that's why we call those zeros. So the zeros are 1, -1, and 6. But because we have a repeating 0, we'll just repeat that 3 times. So again, we have a total of 5 zeros, but one of them repeats 3 times. So what this means, because we need to find the multiplicity of each zero. 1 is a zero of multiplicity 1, and negative 1 is a zero of multiplicity 3, and 6 is a multiplicity, or a zero of multiplicity 1 again. You can see the multiplicity by looking at the exponents. If you're writing the polynomial in factored form with exponents. So we solved the problem. We have the zeros up here, and we found the multiplicity of each zero. Okay, so now let's do one more of these problems before you try one on your own. Now the problem is again stated a little differently. It says use the Rational Zeros Theorem to find the x-intercepts of the function below. So now they're called x-intercepts, but again, zeros, roots, x-intercepts, they're all the same thing, pretty much. There's some slight differences when you're talking about x-intercepts, but generally speaking, we're talking about the same thing. So we're going to find the x values that make this expression 0. Again, those are x-intercepts. So we're going to use the Rational Zeros Theorem as we did in all the other problems. So we're going to find the factors of 36. Whoops, I missed one. I'm on 6. And we have 12 and 18 and 36. I think I got all the factors there. And then 1 and 5. So writing all the factors. 1 divided by 1 is 1. 1 divided by 5 is 1/5. 2 divided by 1 is 2. 2 divided by 5 is 2/5. And we probably don't need to really write very many more of these. There's a lot of these factors, so I'm not going to write, or a lot of these possibilities, possible potential x-intercepts or zeros. So I'm not going to write all of these. I'm just going to write an arrow here that shows that you can just keep going there. I don't think we're going to need all of these. So let's start by plugging in positive 1. We always start with positive 1, and that doesn't work. Now let's try negative 1, and that doesn't work. Again, I'm not going to do these because it would take a while. Let's try plugging in 2. That doesn't work. We'll try plugging in negative 2, and that doesn't work. Again, if we don't get 0 when we plug into this polynomial, it doesn't work. But if we plug in 3, that actually works. So remember the factor theorem, if you plug in 3 to a polynomial and you get 0, that means that x minus 3 is a factor of that polynomial. But we need to find the depressed polynomial, so we're going to write the coefficients. 5, 2, negative 63, and 36. And we're going to divide by x minus 3, which means this number is going to be positive 3. And then we get negative 12, multiply, we get negative 36, the remainder is 0. So that's a good sign. That means that we did it correctly. So x minus 3 times, and let's write the the depressed polynomial 5x squared plus 17x minus 12. We got those numbers from there. And so we're going to write that pink polynomial 5x squared plus 17x minus 12, and now we just have to factor that to find the remaining x-intercepts. So 5 times 1 is 5, and we'll try maybe -3 and +4, and looks like I got lucky. Looks like that works. So we can see the x-intercepts now, because if you plug in 3 to this expression, you get 0. So that means if you plug in 3 to this polynomial here, you get 0. Again, this expression here is just a different form of this polynomial. If you plug in 3/5, you get 0, and if you plug in -4, you get 0. So those are the x-intercepts. Now, you can also call them zeros. If you call them zeros, then we can say 3 is a 0 of multiplicity 1, because there's only one of those factors. 3/5 is a 0 of multiplicity 1, because there's only one of those factors. And -4 is a 0 of multiplicity 1, because there's only one of those factors. So we found the x-intercepts, and we found the multiplicity of each one of those zeros. Again, you can call them zeros or x-intercepts or roots. So now it's time for you to try. I want you to take a picture of all these pages here to help you. And you can take a picture of that page at the 4 pages at the left. And go ahead and try number 11. So we're going to solve this equation. We're going to find how many solutions? Well, 3. There's going to be a total of 3 solutions, because it's a 3rd degree polynomial. Now, some of those solutions might be repeated, so to speak, but we're going to find 3 total, and we're going to start by using the Rational Zeros Theorem to find the first solution. So you're going to write P, Q, and P over Q. So the first thing that I want you to do is to find all of the potential rational zeros. Now, you don't have to write all of them, because there might be quite a few with 30. But I want you to list maybe the first 4 or 5 of those, and then we'll do that together. So that just start that part of the problem, because these problems can be kind of long, and when you come back, we'll do that together. Okay, we're back. So P represents the factors of 30, and Q represents the factors of 4. So we have 1, 2, 3, 5, 10, 15, and 30. Factors of 4 are 1, 2, and 4. And P over Q, we're going to have 1 divided by 1 is 1, and 1 divided by 2 is 1/2, and 1 divided by 4 is 1/4. Again, we're really not going to use the fraction, so 2 divided by 1 is 2, 2 divided by 2 is 1, and 2 divided by 4 is 1/2. We already have those, so maybe we'll do just a couple more. 3 divided by 1 is 3, 3 divided by 2 is 3/2, 3 divided by 4 is 3/4, and we could keep going, but we don't really need all of these. There might be some problems where you could potentially need all of them, but I'm not going to give you problems that are that difficult. So if you got those numbers, good. So now you're going to test some of these. these numbers. So we're always going to start out with 1. So I want you to test 1. Go ahead and do that and see what you come up with, and when you come back we'll do it together. Okay, we're back. So if you plug in 1, you get 4 minus 31 is negative 27, and then negative 27 plus 61 is 34, and 34 minus 30 is 4, so that did not work. And by the way, don't be afraid to use a calculator. It's perfectly fine to use a calculator. So let's try x is equal to negative 1. So go ahead and plug in negative 1 and see what you get. Okay, we're back. So then we have negative 4 minus 31, then minus 61, then minus 30, and we can see that that's not going to work. So that won't work either. Now let's try x is equal to 2. So I'll plug in 2, and when you come back, we'll do it together. Okay, we're back. We get 32 minus 124. That gives us negative 92, and then we're going to add 61 times 2. That gives us 30, and 30 minus 30 is 0. So we found a solution. 2 works. Now, again, the factor theorem tells us that if we plug in 2 and we get 0, that means that x minus 2 is a factor. So we're going to divide this by x minus 2 to make a simpler polynomial. But we're going to use synthetic division because that's just easier to deal with. So go ahead and use synthetic division, and when you come back, we'll do it together. Okay, we're back. The coefficients are 4, negative 31, 61, and negative 30. Okay, so let's do the algorithm. And we get the following numbers, and our remainder is 0, so that's a good sign. So our depressed polynomial is going to be a degree 2 because we started out with degree 3, so it goes down by 1. So now write the new factored form of the polynomial, and when you come back, we'll do it together. Okay, we're back. So what this means is that our polynomial is equal to x minus 2 times the green 4x squared minus 23x plus 15. Now factor the green expression and then see if you can find the solutions to the original equation. When you come back, we'll do it together. Okay, we're back. So if we factor, let's try 2x and 2x and negative 5 and negative 3. That doesn't work. So I have a feeling it's going to be 4 and 1. Let's try 4 and 1. And so we get, well, that doesn't work either, so let's try switching the 5 and the 3. And that works. So now that we have the factored form, we can find the solution or the solutions to the equation. So this works the same way it works when we are solving quadratic equations. We're just changing the form of the polynomial, and then we can see the solutions just by looking at that expression. So 2, 3/4, and 5 are the solutions. We're not asked to actually state the multiplicity, so you don't have to do that. So if you got that answer, excellent. So now I want you to try number 12. The first step is to use the Rational Zeros Theorem to find the potential roots. Now notice it's asking for roots. That's just another way of asking for the zeros. Zeros, roots, and x-intercepts are pretty much the same thing. So use the Rational Zeros Theorem to find the potential zeros. And you don't have to list all of them, but at least list the first 4 or 5. And just do that part first. And when you come back, we'll do it together. All right, we're back. So P is the factors of 18, and Q is the factors of 3. So we have 1, 2, 3, 6, 9, and 18. Those are the factors of 18, and we have 1 and 3. So again, we don't have to list all of these potential zeros, but let's do 1 divided by 1, 1 divided by 3, and 2 divided by 1, 2 divided by 3, and 3 divided by 1, and 3 divided by 3 is 1. We already have that on the list. And we could just keep going and going. But again, I'm not going to make you write all of those because we don't really need all of them. So if you got that right, good job. So now we're going to start by plugging in 1. See if 1 is a root. So go ahead and do that. And when you come back, we'll do it together. Okay, we're back. So if you plug in 1, we have 3 plus 5 is 8, minus 25 is negative 17, minus 45 minus 18, and you can see that that doesn't work. Okay, so now let's try plugging in negative 1. You always try plugging in negative 1. So go ahead and do that. And when you come back, we'll do it together. Okay, we're back. So plugging in negative 1, you get 3 minus 5 is negative 2. And negative 2 minus 25 is negative 27. And negative 27 plus 45 is 18, and 18 minus 18 is 0. So that actually works. So negative 1 is a 0. So I'm going to write that down here. All right, so if you figured that out, good job. So remember, the factor theorem tells us that if you plug in some number and you get 0, then x minus that number is a factor of the polynomial. So we're going to divide by x minus negative 1, which is x plus 1, but you're going to use synthetic division. So go ahead and do that, and when you come back, we'll do it together. Okay, we're back. So I'm going to divide by x plus 1 using synthetic division. And I'm going to move this over a little bit. Let's do our synthetic division algorithm. And our remainder is 0. So that's a good sign. Okay, so now you want to write your depressed polynomial. So if you haven't done that, go ahead and write your depressed polynomial. So the depressed polynomial should be 3x cubed plus 2x squared minus 27x minus 18. So if you got that depressed polynomial, good job. Now we have to check for repeated roots. Negative 1 worked, so it might work again. So now you have to try to plug in negative 1, but you're not going to plug it into the original polynomial. You're going to plug it into the depressed form because that's going to be easier to work with. So go ahead and do that. And when you come back, we'll do it together. Okay, we're back. So if you plug in -1, we get -3 plus 2 is -1, plus 27 is 26. 26 minus 18 is 8, so that doesn't work. So if you said that that doesn't work, then you're correct. So now let's try plugging in 2. We have 2 on the list. We never plug in fractions because that's going to be too difficult. We could do it, it's just too tedious to have to deal with that situation. So now we have 24. Well, why don't you go ahead and plug it in, see if you can do it, and when you come back, we'll do it together. Okay, we're back. So it looks like that doesn't work. So if you confirm that, good job. So now let's try -2. Let's try x equals -2. So go ahead and test that number. And when you come back, we'll do it together. Okay, we're back. So if you plug in -2, we get a -24 plus 8 is -16 plus 54. So -16 plus 54 equals 38. 38 minus 18 is 20, so that doesn't work either. So if you confirm that, good job. So what else can we try? Let's try 3. So we'll try x is equal to 3. So go ahead and try 3, and when you come back, we'll do it together. Okay, we're back. So the first term is going to be 81. The next term is going to be 18. So 81 plus 18 is 99. Minus 27 times 3 equals 18. And 18 minus 18 is 0. So that actually works. So if you confirm that, good job. So now the question is, what do we do? Well, we have to divide by x minus 3. If you plug in 3 and it's a 0, then that means that x minus 3 is a factor. So we're going to divide this by x minus 3 and find a depressed polynomial. Again, that's the factor theorem. So go ahead and do that using synthetic division, and when you come back, we'll do it together. Okay, we're back. So I'm going to write these pink coefficients: 3, 2, -27, -18. And we're dividing by x minus 3, so I'm going to put a positive 3. So let's do the algorithm. And we get 0. Again, if you don't get 0, then that means you probably did something wrong for the remainder. So now we have a depressed polynomial. We started out with a degree 4, so now we're going down, well, we went down to a degree 3, now we're going to a degree 2. So we have 3x squared plus 11x plus 6. Okay, so go ahead and write the new factored form of the polynomial, and when you come back, we'll do it together. Okay, we're back. So therefore, our original polynomial is equal to, and what were the numbers? We had -1 was a solution, so x plus 1 is a factor. And we found that 3 is a solution, or a 0, so x minus 3 is a factor. And we have this blue leftover factor, which is 3x squared plus 11x plus 6. So we're looking for the roots of this polynomial function. And all we're doing is just changing the form of that polynomial so that we can find the roots. Again, the roots are the numbers that you can plug in to make the polynomial equal to 0. You can call them roots, you can call them zeros, you can call them all kinds of different things. So go ahead and factor that blue expression and find the roots of the polynomial function. And when you're done, we'll do it together. Okay, we're back. So 3 times 1 is 3, and 2 times 3 is 6. I'm going to try that. I don't know if it's going to work. So 9x, so yeah, that does actually work. So looking at this new form of the polynomial, we can see the roots. We have -1, 3, -2/3, and -3. And those are the solutions that we're looking for. Now again, we're not solving an equation, we're just looking for the roots. But technically we are solving an equation because the roots are the numbers that would give us 0. So this problem is really solving a polynomial equation, even though we're not actually solving an equation, we're just finding what they call roots. So if you got that right, good job. Okay, so now I want you to try number 13. And we are looking for the zeros of the polynomial, the x values that make it equal to 0. So this is just, again, it's the same problem, just worded slightly differently. And we're going to find the multiplicity of each 0. So at this point, you can take a picture of the previous problems that we did. And you can try 13 on your own. If you want, we can do it in steps together. So use the Rational Zeros Theorem to find the potential rational zeros. Write your P and Q and P over Q values. You don't have to write all of them, but in this case, there's not very many of them. So try that first part of the problem, and when you come back, we'll do it together. Okay, we're back. So P is the factors of 2. Just to be clear, we got that from here. And Q is the factors of 2 also. So P over Q, if we divide, we get 1 divided by 1 is 1, and 1 divided by 2 is 1/2. Then we're going to divide 2 by 1, and we get plus or minus 2, and divided 2 by 2, we get positive 1, plus or minus 1, but we already have that on the list. So that didn't take very long to list those potential rational zeros. So if you got that right, good job. Now you want to test those. So we're obviously going to start by testing 1. So go ahead and plug in 1 and see what you get. Okay, we're back. So if you plug in 1, you get 2 minus 1 is 1, minus 7 is -6, minus 1 is -7, plus 5 is -2, and -2 plus 2 is 0. So that actually worked. So if you confirmed that, good. So now what do we do? Well, if you plug in 1 and you get 0, that means x minus 1 is a factor of this polynomial. That's the factor theorem. So you're going to divide by x minus 1, but we're not going to use long division, we're going to use synthetic division. So set up your synthetic division and see if you can do that. And when you come back, we'll do it together. Okay, we're back. So let's do the synthetic division. The coefficients are 2, -1, -7, -1, 5, and 2. And we're dividing by x minus 1, so we're going to put a positive 1. And the remainder is 0, so that's a good sign. So now we're going to write our depressed polynomial. We started out with a degree 5 polynomial. Now we go down to a degree 4. So if you got that right, good job. So now what do? Well, you're going to plug in another number. Using these numbers here, you're going to plug in another number to your depressed expression and see if you can find another 0. So go ahead and do that. We know that 1 works, but 1 could be a repeated 0. So you want to find a possible repeated 0. So plug in 1 again and see what you get. And when you come back, we'll do it together. Okay, we're back. So 2 plus 1 is 3, minus 6 is -3, minus 7 is -10, minus 2 is -12, so that doesn't work. So if you ruled that out, good job. Now we're going to try x is equal to -1. We haven't tried that yet. So go ahead and plug that into the depressed polynomial, see what you get. When you come back, we'll do it together. All right, we're back. So we get 2 minus 1 is 1. 1 minus 6 is -5. -5 plus 7 is 2, and 2 minus 2 is 0, so that actually works. So if you confirm that, good job. So now what do? Well, because -1 is a 0 of this depressed polynomial, the factor theorem tells us that x plus 1 is a factor of this depressed polynomial. And so if we divide by x plus 1, we'll get a polynomial that's even more depressed. So go ahead and do that. Use synthetic division, and when you come back, we'll do it together. All right, we're back. So let's write the coefficients. And we'll divide by x plus 1. And our remainder is 0, so that's a good sign. So let's write the depressed form. We started out with, we had a 4th degree, so we're going to go to a 3rd degree. So we got those numbers from there, obviously. And now we can take that depressed polynomial and move it up. And at this point, sorry, my computer's going slow. At this point, what do? Well, we see if we have any repeated roots. We can plug in -1 again. So do we have repeated zeros? And I should probably put a question mark here. So we're going to plug in -1 again to the depressed polynomial. So we get -2 minus 1 is -3, plus 5 is 2, and 2 minus 2 is 0, so that actually works. So we have a repeated 0. So now I want you to use synthetic division. If -1 is a 0, then that means x plus 1 is a factor, and we can divide by x plus 1 and find another depressed polynomial. So go ahead and use synthetic division, and when you come back, we'll do it together. Okay, we're back, so we're going to divide by x plus 1. Our remainder is 0, so that's a good sign. And I'm going to throw this over here so we have more room. So now our depressed polynomial is going to be a degree 1 less than what we had in the previous step. So therefore, our polynomial, our original polynomial, so we found that 1 worked and -1 worked twice. So if 1 works, then we have x minus 1 is a factor. If -1 worked twice, then we have x plus 1 twice. And we're left with the green 2x squared minus 3x minus 2. So now all we have to do is factor that green quadratic. So let's try -1, and I'm going to put the 1 on the other side actually. And that doesn't work, so we're going to have to change the signs, change that to a positive, change this to a negative. And there you go. So now that we wrote it in factored form, and by the way, we can write it in exponential form if we want to. We can see the zeros. We have -1. Actually, let's do it from left to right. We have +1. We have -1 twice, -1/2, and then 2. So we have a 5th degree polynomial, and we have 5 roots if we consider this repeated root twice. So 1 is a 0 of multiplicity 1. -1 is a 0 of multiplicity 2. And -1/2 is a 0 of multiplicity 1, and 2 is a 0 of multiplicity 1. So if you got that right, excellent. Okay, so now we have one more problem to do. Go ahead and try 14. See what you can do on that one, and be aware there's going to be a lot of repeated roots, I believe, for 14. So try number 14, and when you come back, we'll do it together. Okay, we're back. So the factors of 1 are 1. And the factors of 6 are 1, 2, 3, and 6. And if we divide 1 by all these numbers, we get plus or minus 1. 1 divided by 1 is 1. 1 divided by 2 is 1/2. 1 divided by 3 is 1/3. And 1 divided by 6 is 1/6. So hopefully we don't have to deal with these fractions. So we're just going to try plugging in 1. And we'll see what we get. So we have 6 minus 19, which is negative 13, plus 17, which is 4, plus 2, which is 6, minus 8, which is negative 2, plus 1, which is negative 1, plus 1 is 0. So that actually works. Okay, so we're going to use synthetic division. So we have 6, negative 19, 17, 2, negative 8, 1, and 1. And we're dividing by x minus 1, so it's going to be positive 1. And the remainder is 0, so that's a good sign. So we have the depressed polynomial 6x to the 5th minus 13x to the 4th plus 4x cubed plus 6x squared minus 2x minus 1. So obviously we get those numbers from there. Okay, so now we're going to check for repeated zeros. So we're going to check x equals 1 again. But now we're going to plug in here. So 6 minus 13 is negative 7, plus 4 is negative 3, plus 6 is 3, minus 2 is 1, 1 minus 1 is 0. So that works again. So remember, I said there's going to be a lot of repeated zeros for this. So what that means is we can divide that pink depressed polynomial by x minus 1 again. So let's do that. And we get 0, so that's a good sign. That means we did it correctly. Let's write the depressed polynomial. So now we have a 4th degree polynomial, 1 less than the degree in the previous step. And so now we're going to check for repeated zeros again. So let's plug in 1 again. So I'm going to move this down a little bit. Let's try x equals 1 again. So 6 minus 7 is negative 1. Negative 1 minus 3 is negative 4. Negative 4 plus 3 is negative 1. Negative 1 plus 1 is 0. So that works again. So now we know that we can divide by x minus 1. And let's write the blue coefficients: 6, negative 7, negative 3, 3, and 1. And let's make sure we wrote those right. So let's do the synthetic division algorithm. And our remainder is 0, so that's a good sign. So now we have another depressed polynomial. Now we have a degree 3. So we got those numbers from there, obviously. And so now let's check for another repeated 0, because we need to go all the way down to a degree 2 polynomial. So let's try x equals 1 again. So 6 minus 1 is 5, minus 4 is 1, 1 minus 1 is 0. Again, we just have a lot of repeated zeros for this problem. So now we're going to use synthetic division again, and we're going to divide that green polynomial by x minus 1. And so let's do the algorithm. And we get 0, so that's a good sign again. And now let's write the depressed polynomial. So 6, now we're going to a second power polynomial, or a degree 2 polynomial. So what this all means is that original polynomial that we had is equal to x plus 1, actually x minus 1, because positive 1 was a solution, or a 0. X minus 1 times x minus 1 times x minus 1 times x minus 1. We found that that was a root, or a 0, or an x-intercept that repeated 4 times. And then we're left with the 6x squared plus 5x plus 1 at the end. So we can write that x minus 1 in exponential form, obviously. Actually, let's just copy it for now. And let's factor. So what are two numbers that multiply to 6? We can try maybe 6 and 1. I don't know if that's going to work, but we can try it. And looks like that's not going to work. So let's try 2 and 3. And 1 and 1. So then we get 5x in the middle. So that does work. So therefore, the x-intercepts, well, let's write this in exponential form, might as well. So we can put all those x minus 1s together, and that'll help us to see the multiplicity. Again, the multiplicity is the powers, the exponents of each of these factors. So the x-intercepts are 1, negative 1/2, and negative 1/3, because if you plug those in to the polynomial, you get 0. So 1 is a 0 of multiplicity 4, because there's a 4th power there. And negative 1/2 is a 0 of multiplicity 1, because there's only one factor that comes from there. And negative 1/3 is a 0 of multiplicity 1 also, because the power is 1. There's only one factor. So if you got that right, excellent. So we found the x-intercepts, and we found the multiplicity of each x-intercept. And so again, if you got that one right, good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2, number 3, 4, 5, 6, 7, 8, 9, and 10. But don't go before you get your homework. Here's the homework assignment. Remember, if you don't do the homework, it's 100% guarantee you're going to learn absolutely nothing in the entire course. Here's the second screenshot for the homework. And the third screenshot. And it's not enough just to attempt the homework. The homework must be correct. So make sure that you have these answers. Get this screenshot so you can check your work. So again, the homework is not optional. You must do the homework. So get that done and be sure to keep it in order in your binder. And I'll look forward to seeing you in the next class.